This is a good point to start to think about some other forms of utility functions. Let's take a look at a few graphical examples. The first example is what we call perfect substitutes. And this is a utility function that has very simple indifference curves. They are just straight lines. So how would we express such indifference curves in the form of a function? Well, we would simply write the utility is equal to the amount of good 1 multiplied by some kind of constant I plus the amount of good 2 multiplied by another constant j. For example, if I and j are both 1, then the utility function becomes particularly simple, which is just q1 plus q2. But now guess what? Once we have this utility function, q1 and q2 can be perfectly swapped by each other. And this is what I mean by that. If I have 4 units of good 2 and no units of good 1, or the other way around, or 1 unit of good 1 and 3 units of good 2, or 3 of good 1 and 1 of good 2, or 2 of each, all of these combinations are simply going to give me exactly the same amount of utility of 4 units. And that's coming from this utility function. What you realize is that because the utility value is simply the sum of the two quantities, we can just move these quantities between these two buckets of q1 and q2. As long as the quantities in total are the same, the utility value does not change at all. And the property associated is precisely substitution, and in fact a perfect one, because we can perfectly replace 1 unit of good 1 with 1 unit of good 2. One good example of that is to think of them as cans of Pepsi and cans of Coca-Cola. If you're not a particularly astute consumer of soda drinks, you might not be able to tell the difference between them. And in that case, you can simply give me 1 can of one product or the other. They're all indifferent to me. Now, to generalize that idea a little bit, we don't necessarily have to have I and j equal to 1. We can have I and j taking different values. You might think of an environment where you can have the same kind of item contained in different volumes or different sizes. I may have a bottle of water that is 32 ounces, and I can have another bottle of water which is 16 ounces, exact half of the first kind. So now, if we have a 32-ounce bottle and 2 16-ounce bottles, they would have given me exactly the same kind of utility. So how do we represent that? Well, if I is 1 and j is 2, then the utility function would be q1 plus 2 times q2. Then, in that particular case, 2 units of good 2, the larger size, is going to be the same as 4 units of the smaller size, which is going to be the same as 1 unit of the small one and 1.5 unit of the big one, or 3 of the small one and half of the big one, or 2 of the small one and 1 of the big one. And again, they all have the same utility value of 4 units to me. What is the shared property between this example and the previous one is that we're able to replace one good with a certain amount of the other good perfectly. And the rate at which we can replace them do not change at all, unlike our previous observation that we made from the Cobb-Douglas utility function, where as I get more and more and more of good 1, it becomes increasingly difficult to replace q2. Here, that's not a problem at all. You can always replace 1 unit of good 2 by exactly the same amount of good 1, although that amount might not be 1 unit, depending on the value of I and j. This feature is also captured by our figure here. If you focus on the downward sloping indifference curves, they're straight, which implies that their slopes are not changing at all. And that's exactly the intuition I was trying to describe just now. Now, because the marginal rate of substitutions are not changing, the rate at which you can replace one good with the other is not changing at all. It doesn't matter if I have few units of good 1 or a lot of units of good 1. They all give me exactly the same rate at which I can replace good 2. Of course, this is somewhat of an extreme form of a utility function. Now let's try to take a look at another extreme. And this is our panel B here, which we'll call perfect complements. You will notice that these indifference curves are perfectly angled at 90 degrees. So all look like elbows that's sort of bent in this way and pointing towards the origin. To see how these elbow-looking indifference curves correspond to the notion of perfect complements, let's focus on this particular indifference curve here. Now we have several consumption bundles along the same indifference curve. They share the property that they all have the same amount of pies, but they differ by the amount of ice creams they have. But by sitting on the same indifference curve, the graph is telling us that bundles A, D, and E all give this consumer exactly the same amount of utility. So how do we interpret that? So with one slice of pie, it doesn't matter you give this consumer 1 scoop of ice cream, 2 scoops of ice cream, or 3 or 4 or 5, etc. The consumer has exactly the same amount of utility. Well, if this is a consumer who must enjoy 1 slice of pie in combination with 1 scoop of ice cream in that perfect proportion, then that will be what their utility look like, because the extra scoops of ice cream just has no use for them. And similarly, if the consumer only has 1 scoop of ice cream, then it doesn't matter how many slices of pies you give to this consumer, they all bring exactly the same amount of utility. So how do you increase utility for this consumer? Well, if the consumer has to enjoy pie and ice cream in perfect proportions, then the only way to increase utility is to give them these 2 goods simultaneously. For example, 2 slices of pies and 2 scoops of ice cream, or 3 and 3, or 4 and 4. You get the idea. Because the consumer cannot enjoy one good without consuming the other, these 2 goods must go hand in hand in perfect terms, and this is the notion of perfect complements. So how do we write such indifference curves in the form of a utility function? Well, it's going to look like the following. The utility value is simply the minimum between some scaled versions of Q1 and Q2. And again, they're just simply scaled by some constants I and j. For example, if I is 1 and j is 1, then the utility function will look like the minimum between Q1 and Q2. So if you take the example of ice creams and pie, then if the consumer has no pie and 4 units of ice cream, or 4 units of ice cream and 0 units of pie, or 1,000 slices of pie and no ice cream, or the other way around, the consumer will just have 0 unit of utility. Why is that? If you take the minimum between 0 and 4, it's 0. You take the minimum between 4 and 0, it's 0. You take the minimum between 1,000 and 0, it's 0. You get the idea. And that's exactly the function that generates this type of indifference curves we've just seen in this example. So how do we have a positive amount of utility? Well, if you give this consumer 1 slice of pie and 1 scoop of ice cream, or 1,000 slices of pie and 1 scoop of ice cream, the minimum between them is going to be 1. So the consumer will have 1 unit of utility, exactly the indifference curve that we're trying to draw here. What if I and j are not necessarily exactly the same value? Well, again, just like I and j in the perfect substitute case don't have to be 1 and 1 all the time, the I and j in the perfect complement case don't have to be 1 and 1. And that is where you need one good to go hand in hand with a different amount of the other good. For instance, we might have I is equal to 1 and j is equal to 2. In that case, 1 unit of good 2 is going to give us 2 units of extra utility, only if you give us 2 units of good 1 to go with it. To see how that works, for instance, if Q1 is 0, Q2 is 2, the minimum is between 0 and 2 times 2, which is 4. And similarly, the utility between 4 and 0 is the minimum between 4 and 2 times 0, which is 0. So the result is 0. Similarly, the minimum between 1,000 and 2 times 0 is 0. So they all have the same 0 amount of utility. It doesn't matter how much of the other good I have, as long as I don't have this good, my utility is 0. Now, if I have 1 unit of good 1 and 1 unit of good 2, then I'll be taking the minimum between 1 and 2, and that will give me a utility of 1 unit. If I have 1,000 units of good 1 and 1 unit of good 2, then I'll be taking the minimum between 1,000 and 2 times 1, and the minimum will be 2. So what would be an intuitive example when I is 1 and j is 2? Can you think of any? Well, one example is bicycles. You need 2 wheels to go with the frame. So if Q1 is the number of wheels you have, and Q2 is the number of bicycle frames you have, then you will have to have them to go in the ratio of 2 to 1. In other words, if I have 2 wheels, which is Q1, and 1 frame, which is Q2, then my utility level would be the minimum between 2 and 2, which would be 2. How do I increase the utility level from there? Can you think about that? We'll come back to this question later on when we think about the consumer's problem. Well, as a technical note, you might ask, what is the marginal rate of substitution for the indifference curves of perfect complements? Well, the marginal rate of substitution is going to be infinity on the vertical stretch and 0 on the horizontal stretch. And it is going to be undefined at the kink because marginal rate of substitution is defined as a slope, which in turn depends on derivatives. But this function here with a sharp turn and a kink is not differentiable at the kink. Intuitively, the amount of change you need to make to Q2 when you increase Q1 slightly at this kink is neither infinity nor 0, nor any value in between. We don't really know what it is, but it only happens at that particular point. But this sort of unknown, awkward situation only happens at that particular point. Although we're unable to calculate the marginal rate of substitution in a meaningful way for these indifference curves, it turns out that we're still able to solve consumer's choice problem, even if we have this type of utility functions. We'll get back to this later. In general, most indifference curves will look somewhere in between of these two extremes. For instance, this curve here looks very much like an indifference curve of a Cobb-Douglas utility function. They would be more curved comparing to the straight indifference curves, but much more smooth than these perfectly angled, perfect complement indifference curves. The intuition behind this is that in fact any kind of indifference curves that look smooth and bends down like that carries both the properties of substitutes and complements simultaneously. On the one hand, we're able to replace one good with the other while maintaining the utility level, which is not happening with perfect complements. While on the other hand, the replacement isn't perfect, unlike in the perfect substitute case. And that is the notion of diminishing marginal rate of substitution we mentioned previously. So in general, we can think of perfect substitutes and perfect complements as extreme versions of general utility functions, and think of the indifference curves coming from more common utility functions as a spectrum that lies between these two extremes while sharing some properties of both. Now at this point, you will usually see in academic economic literature that people refer to this kind of particular shape as a convex curve. This is in fact a mathematical concept that tries to define a set of properties about the way a particular function looks. The notion of convexity and its opposite, concavity, are very important notions in economics. So now let's try to introduce these concepts in slightly more abstract but more general form. We just mentioned that usually indifference curves tend to take a shape that bends downward towards the origin. Well, that is a mouthful to describe about a particular function. It turns out mathematicians have a name to describe this type of features, and it's called convexity. And convexity has an opposite notion that is called concavity. These are both notions we use to describe functions. So what do we mean by them specifically? Well, the idea is really quite simple. Let's say I have a simple function like this, which increases from the origin and then bends downward like that. So how do we describe this feature? Well, one way to think about it is that if I pick any two arbitrary points along this curve, and then thread a line across these 2 points that I just chose, will this line lie above or below this particular curve? If you think about this curve, it doesn't matter how you choose the starting point and the end point of a segment. After connecting them, the segment is always going to lie below this curve itself, regardless of how you make the choice. If the function passes this particular test, we will say the function is concave. And in particular, if the segment always lies strictly below the curve itself, we're going to say the function is strictly concave. And if the segment sometimes lies on the curve itself and sometimes below, we're going to call it weakly concave. To the opposite, if I have a function that looks like this, and we do the same test of picking any 2 points and thread a line through them, what we'll realize is that connected segment is always going to lie above this particular function, regardless of your choice of starting and ending point. And in that case, because the segment always lies above the curve, we'll call this function convex. And similarly, if the segment always lies strictly above the curve itself, then we're going to say the function is strictly convex. But if the curve sometimes lies above it, and sometimes on the curve itself, then we're going to say it's weakly convex. But not all functions only passes one of these tests. For instance, if we have a straight line like this, and we run the same test by picking any 2 arbitrary points along the curve and connect them, then the segment in between is always going to lie on the curve. Well, then it is both above and below the curve in the weak sense. So in that case, a straight line is in fact both concave and convex simultaneously, although in a weak sense. And in fact, not all functions would pass one or the other of these tests. You might have a case where it passes neither. For instance, take this function that increases, but first of all, it bends down, and then later on, it sort of bends upwards. Then it will depend on which kind of points we pick. The segment that is thread through these 2 points would sometimes lie below the curve, sometimes lie above the curve, and sometimes just crosses through the curve itself. In this case, the function is neither concave nor convex. The notions of concave and convex functions are used widely in economic theory to describe many different kinds of functions we use in economic modeling. And they give us different properties that are usually very desirable. That makes our analysis easier. And when it comes to indifference curves, what you will notice is that indifference curves in economic theory are always convex, at least in the classical theory that was studied within the scope of this course. And these indifference curves give us very nice properties that we have been thinking about thus far, which captures quite a bit of intuitive and realistic features of people's preferences. And on the graph form, we'll just see that it doesn't matter if they're downward sloping and straight, or bends aggressively like this, or slopes downwards in a smooth way. They're all convex. And you can try picking any 2 points and connecting them into a test on each one of them. Now, in addition to Cobb-Douglas utility functions, there are at least 2 other utility functions we would like to introduce to you. because they're being applied widely in many different scenarios. One important utility function is what we call constant elasticity of substitution, which has a shorthand of CES. Another utility function that is used widely is called a quasi-linear utility function. Now let's take a quick look at each one of these additional types of utility functions. First, let's talk about constant elasticity of substitution utility function, and we'll refer to it later on as CES utility function. This utility function, again, is simply a scanner of the quantity of two different goods, Q1 and Q2, in a consumption bundle. And the function is evaluated as such. We're going to take Q1 and raise to the power of rho, which is just like alpha in the Cobb-Douglas utility function, which is just a constant. And then we're going to add that with quantity of good 2, Q2 raised by the same power of rho. And then we're going to take the sum and raise the sum by the power of 1 over rho, the reciprocal of the power inside. Rho here is just a constant, but it cannot be 0, and it is restricted to be less than 1. What would happen if rho is 1? Well, then the outside power just becomes 1, and the inside powers also just become 1. So the utility function is just Q1 plus Q2. That reduces to our very familiar perfect substitute case, where you can perfectly replace one good with the same unit of the other good. One quick note is that you cannot simply distribute the power of 1 over rho into this function and just cancel out power rho with power of 1 over rho. To see that, if we have a function x plus y, each raised to the power squared, and then take a square root of this, is this equal to x plus y? Well, no. If x is 1 and y is 2, then the left-hand side, which is square root of x plus s squared plus y squared, and then taking square root over, is going to be the square root of 5. But what x plus y is going to be 3, and clearly they're not equal to each other. If you're tempted to do that, you're confused between this particular expression with the expression of x to the power of 2 times y to the power of 2, and then raised to the power of 1/2. In that case, yes, you will be able to distribute the power into the products, but not to the sums. So back to our particular utility function, this is in fact a complicated expression that does look a little bit daunting, but we're going to work with it a little bit and see that it is in fact not too terrible. And in fact, this utility function gives many desirable properties that Cobb-Douglas utility function simply does not provide. As of the name of this particular utility function, it is because there is a measure which is called the elasticity of substitution. And note that that measure is not the same thing as our familiar notion of marginal rate of substitution here. And it turns out this particular function has the property that its elasticity of substitution is always constant. But we will not talk about that feature now and postpone it until the latter part of the semester. So for now, we're just going to take the name as given, and we're going to call this function the CES utility function. Now, as a good warm-up exercise, let's calculate the marginal rate of substitution for the CES utility function. So how do we do this? Well, we've done it for a bunch of times with Cobb-Douglas utility function. We'll just follow exactly the same approach. We know that the marginal rate of substitution is simply minus the ratio of marginal utility between the two products. So we're going to break the task down to 2 steps. First, calculate the respective marginal utilities for good 1 and good 2, and then take the ratio. Let's do this. If we calculate the marginal utility of good 1, we're going to take derivative of this utility function with respect to Q1. Again, treating Q2 as constant. So now, this involves the use of chain rule. because you can see the inside sum as a function of q1 and q2, and then it is the inside function, which is the sum, raised by the power, which is the out layer of the function. Now, as a quick refresher of the chain rule, if we take derivative of a function that is wrapped around by another function with respect to x, what happens is we're first going to take a derivative of the out layer function with respect to whatever is inside it and treat that as a bundle that is moving the outside function. And then we're going to multiply that by the derivative of the inside function with respect to x. And here in this case, we're using z as a placeholder for the function of f of x. So in fact, we're going to take a derivative of f of x here with respect to x. All right, let's get to work here. In this particular case, what is our inside function? Now let's translate the CS utility function into this nested function format. Our inside function is a function of both q1 and q2, and it is simply the sum of these two quantities. The outside layer, or g of z, is simply to raise whatever comes into this function by the power of 1 over rho. So in fact, our CES utility function can be written as a combination of these two functions. It is just g wrapped around f of q1 and q2. Does that make sense? Once we start to see the function in this form, the derivative will follow from the chain rule implied above. We're going to first take derivative of g with respect to whatever is inside. Effectively, we're going to take derivative of this function first. In other words, the derivative of u with respect to q1 is first taking derivative of g of z with respect to z. And then we're going to multiply it by the derivative of z with respect to q1. But what is z now? Well, z is just the inside function, which is f of q1 and q2. It is a useful placeholder, especially when we calculate the derivative of the out layer function of q. Now let's see how that looks like. The derivative of the outside layer function, z raised to the power of 1 over rho, is very straightforward. Again, if you see z as x, it's just power rule. The power of 1 over rho comes down, and the power on z becomes z to the power of 1 over rho minus 1. And then we're going to multiply by the derivative of z, which is f of q1 and q2 with respect to q1. What is that? Well, that is just working with this expression down here. We're going to take derivative of this expression with respect to q1. And because this expression is a sum between q1 and q2, where q2 is treated as a constant, the constant part that is added to it is just going to drop out. And what we're left with is effectively only q1 to the power of rho. So the derivative of f, which is this part, with respect to q1, is simply going to be rho times q1 to the power of rho minus 1, which is our second part of this expression here. Now, what is the first part? Where did that come from? Well, we already have that in place. It is hiding right here. Remember, z is simply the placeholder we used to replace f of q1 and q2. It is just a wrapped up bundle. Let's write it down. What is z? Well, it is just f of q1 and q2 raised to the power of 1 over rho minus 1. But what is f? Well, it is simply q1 to the power of rho plus q2 to the power of rho. And now we have it. This is exactly the expression we have here on the right. Now you can simplify this a little bit, because what we realize is that we have a rho here and we have a 1 over rho in the front. So they will just cancel out and the expression just becomes slightly simpler. It isn't as pretty as the marginal utility with the Cobb-Douglas utility function, but let's bear with it for now. Similarly, we can do the same calculation for the marginal utility of good 2. The calculation is exactly the same, just by swapping out q1 and replace it by q2. Do exactly the same exercise. It is helpful, and please try it so that you can convince yourself that you're able to do this. And hopefully you will arrive at exactly this same expression as what I have here. Now, what we can do is just to follow the two-step approach, plugging in u1 and u2 into the appropriate slots for the marginal rate of substitution and add a negative sign in front. And there we have the marginal rate of substitution. As ugly as this expression might look at first, you will quickly realize that this mumbo-jumbo in the front is exactly the same as a mumbo-jumbo in the front of q2 raised to the power of rho minus 1. So these two terms will just cancel out with each other. Magic! Voila! Suddenly, the marginal rate of substitution simplifies to something very simple, which is just minus of q1 over q2 raised by the common power of rho minus 1. Well, this will do the job, but if you're obsessive like I am, we can rewrite it slightly because now the power of rho minus 1 is actually less than 0. So to make it positive, we can pull out a negative sign to make it become 1 minus rho. But then we can subsume the negative power into this ratio by flipping the order of q1 and q2. And that's exactly this expression here. Now that is how we calculate marginal rate of substitution for a CES utility function. It's not too bad, is it? In time, you'll get used to it, and you'll realize that it is just a set of procedure you need to follow. With your algebra skill improve and getting comfortable with notations we use in this class, these things will become relatively straightforward. Now let's take a look at a different utility function, what we call quasi-linear utility function. And this type of utility function, again, is just a meter of q1 and q2, is taking this particular form. It is a function of q1, which is usually nonlinear, added by q2 by itself. So this function is linear in q2, but not linear in q1. Therefore, its name of quasi-linear utility function. Usually, u here is an increasing and concave function. What that means is as I have more of good 1, my utility is going to increase, but the rate of increase is going to decline as I have more and more and more good 1. If you think back to our graph of a concave function, the shape of downward bending curve would describe this type of property. Now coming back to the quasi-linear utility function, let's try to calculate its marginal rate of substitution. Again, we're just going to break down the task into 2 steps, calculating marginal utilities and then take the ratio. The marginal utility of this utility function with respect to q1 is straightforward, and again, treating little u function here as an inside function, whereas the sum as the outside function, the derivative of the function using the chain rule is just the derivative of the little inside function here, u, which we haven't specified yet, so we cannot really calculate that particular derivative, but we're just going to write down that the marginal utility of good 1 is simply the derivative of this inside wrapper function of u. I'll give you a specific example on the next slide, but for now, let's hang on to this. The marginal utility of good 2 is very straightforward. It is just derivative of u of q1 plus q2, but because q1 is treated as a constant as we vary good 2, and therefore u of q1 is a constant. So it drops out from the derivative, and the result is simply 1. Every unit of good 1 we add to the consumption bundle, there's going to be a 1 unit increase in the utility function. You can simply see that from this utility function here. So, in fact, the marginal rate of substitution for the quasi-linear utility function is particularly simple. It is just the marginal utility of good 1 with the negative sign in front. And that's it. Now let me give you an example of a particular quasi-linear utility function. Let's say we have a quasi-linear utility function where little u here is just raising q1 to the power of 1/2. In other words, we're just taking square roots of q1. Then the marginal utility of good 1, or little u prime here, is simply 1/2 times q1 raised to the power of minus 1/2. This algebra should be familiar by now because we've done exactly the same thing when we calculated marginal utility with Cobb-Douglas utility function when q1 has a power of 1/2. This is more or less exactly the same calculus as before. Now, because the marginal rate of substitution is just minus of this little derivative here of the square root function, so the marginal rate of substitution is simply this. Let's take another example where the quasi-linear utility function is wrapping q1 with the little log function. Now we have log of q1 plus q2. So the marginal rate of substitution by our previous general formulation, again, is just minus of the derivative of this little wrapper function. And because the derivative of log of q1 with respect to q1 is just 1 over q1, so this is our marginal rate of substitution. It's not bad at all. A much easier task comparing to the CES utility function case. We have spent a lot of time trying to understand the notion of modeling preferences in terms of indifference curves, and then try to figure out ways to help us manage and work with indifference curves, where we start to use the tools of utility functions. And from there, we start to study the properties of utility functions and how they relate to the slopes of indifference curves. We worked with Cobb-Douglas utility function, perfect substitutes, perfect complements. We talked about the notion of concavity and convexity of different functions. And we worked with CES utility function and quasi-linear utility function. All of these different things are very useful tools in our modeling toolkit. And we'll see them appear in different applications in this course and beyond in more advanced classes. So for now, we're going to depart from utility temporarily to shift our focus to a different part of the consumer's choice problem, which is the amount of limited resources available to the consumers. And once we have that part, we'll put that part together with the utility component, which is really the heavy part of the machinery. And then with these two components together, we will be able to start thinking about a model of consumers' choices, given their preferences and their resources.